We've got a really exciting project that we want to share with you today. It is about using simulation modeling to improve the profitability and reliability of a steel manufacturer. Probably, as you know, steel manufacturing has been facing some real tough challenges over the past couple of years. Every time that the commodity prices go down, they are really harmed by it. And we were privileged to be involved in this project. We've been working on it for around a year and a half now. First, just a brief introduction of Goldwood Research Labs. We are extremely passionate about helping individuals and organizations make better, faster decisions when it really matters. Not all decisions are consequential. Specifically for organizations, it's about decisions related to how much better can you do? And what's the best way of doing it? What's the fastest, simplest, lowest cost, and lowest risk way of doing much better, achieving a step change in performance? We're very privileged to work with some leading organizations around the world. Many of those we have joint research labs where we work with them to see how to achieve a next step change and improvement. We also work with a couple of research partners. So let's start in terms of the overall outline of the presentation. We'll share the project introduction and the business challenge and why simulation and specifically why AnyLogic. And then we'll do demonstrations of 3 models that we've built as part of this project. We actually ended up building 4 models. We'll demo 3 of those. I will do one of them, the steel supply chain, and Jaco-Ben will be presenting the other 2, the hot coil finishing and the steel and slab plant, and then we'll open it up for some questions. So let's fall right in. The project background, it's one of the largest European steel manufacturers, one of the oldest ones around. Like most steel manufacturers, very much under pressure to improve profitability, to provide a good return on capital for their investors, and at the same time to improve dramatically the service levels. Many of the past improvement initiatives and investments didn't achieve the expected return on investment and improvement in service levels. And it's almost across the industry. If you look at what the service levels and availability they are achieving, they are struggling to achieve more than 80%. And from a customer perspective, of course, that means that you're simply just unreliable. 20% unreliability is unreliable. It only starts making a difference once you get into the high 90s. And lastly, the strategy to improve profitability and asset utilization has all been around high asset utilization, trying to maximize the utilization of every single resource, trying to minimize costs across the supply chain, and their interpretation of applying theory of constraints, like many other industries, unfortunately, resulted in debottlenecking. A good application of theory of constraints means you have a stable system with a single constraint and sufficient protective capacity and buffers upstream and downstream to ensure that that constraint is never starved or blocked, to maximize the throughput and minimize the cost. When you do debottlenecking, you get exactly the opposite. You get unstable systems with interactive constraints, moving bottlenecks, essentially a chaotic system that cannot be reliable and to which you cannot make reliable commitments or predictions. So what specifically was our project objectives? We've got a strategic partnership with this company. It's one of the projects that we do that we are incentivized by the amount of additional profits that we generate. So there's real skin in the game for myself and my team, together with their management team. And we soon realized that the level of complexity that they are facing across that supply chain required the development of simulation models to help them make better, faster decisions and make better, faster predictions, and turn those predictions into reliable commitments to investors and customers. Specifically, we wanted to see, could we use decision support technologies like simulation to identify accurately what the main causes were of past performance gaps, both operational and financial? And could we use it to determine the likely operational and financial impact of changes in rules or investments that they were planning. And lastly, identify potentially some of the global optima rules that are often very counterintuitive from a local perspective. I'm sure many of you have seen that experiences. What is required to optimize a subsystem is very often the exact opposite to what we require to optimize systems. And those global optima rules are often very counterintuitive. The simulation models help us to build intuition around what those rules are. So as I mentioned, we ended up developing not just one, but 4 models. This is what a steel-making supply chain typically looks like. This project, as I mentioned, included ultimately 4 models. The 3 that we will be showing you today is one that is dealing with the steel-making side, the other one dealing with the hot coil finishing side, and then the last one, which is an overall supply chain model, absolutely end-to-end from purchasing of the raw materials all the way through to the service centers and even into the customers to see what order fulfillment strategies should you be making to availability, making to order, making to forecast, what's the best order fulfillment strategy. So what's a business challenge that this management team faced, like many others, is that they are responsible at every level in the organization to make reliable commitments and to judge the impact of changes that are being made or which they are proposing. Secondly, they have to decide what rules to use to optimize the system, not just their subsystem. Why is this challenging? Because more and more these managers are facing what is referred to nowadays as VUCA. I've added in another C, so that describes the full level of issues that makes making decisions and predictions so hard. There's increased volatility, uncertainty, complexity, there's constraints, and on top of that, there's ambiguity in terms of what exactly is the objective that we're trying to achieve. We want it to be effective, efficient, and compliant. Well, which one do you want me to be? In such systems, changes can have nonlinear impacts, as you know. And this has 2 profound implications, both of them often resulting in people resisting change. People will resist change when they don't have the intuition to predict the outcome of that change. The safest way then is to find reasons not to make changes. The second part is that if big changes result in big outcomes and small changes result in small outcomes, then I would feel safe to at least make some small changes. But what if a small change can have a big outcome, either positive or negative? Can you see that it would make us terrified to even make small changes? And that's what we see with systems that are nonlinear. A small change can have a big outcome, both positive and negative. Those things both contribute to managers feeling more and more pressure not to make any significant changes in the environment. So why are the current tools that managers have available not adequate to deal with these challenges? Firstly, as many of the other presenters have shown, is that ERP systems were never designed to really support management decision within complex environments. It cannot fully consider all the interdependencies, all the constraints, all the dynamics around it, all the variability. It simply wasn't designed to do that. And the same with Excel spreadsheets. It wasn't designed to do that. It cannot fully consider it. And even when simulations have been used in the past, what we've seen is they were deep dives into subsystems. We need to understand how to manage and optimize systems, not how to manage and optimize subsystems. So that's why simulation, especially in this type of project, is really the only solution out. It can consider all the critical system interdependencies, constraints, complexities, and variabilities. Of course, it's no easy task to know which are critical and which are not critical. That takes time and intuition, like most of you know. It also can provide a range of outcomes, understanding the stochastic nature of the systems that we're dealing with. When we're running single experiments, we can use it to do sensitivity analysis on parameters that we expect might be sensitive or not sensitive, and we can do direct scenario comparisons. it can also provide a low-risk, low-cost way, essentially, of doing experiments. Today, we talk about creating a culture that is safe to fail. But in many organizations, it's not safe to fail. You fail, you get fired, or at least not get promoted. Virtual environments is a great, safe way to fail. We can do multiple experiments very quickly and learn from our experience. So why specifically AnyLogic? We have seen that AnyLogic has the ability, more than any of the other tools that we've used, to very quickly model real-world complexity, provide incredible flexibility around us, give us the ability to do agent-based modeling, discrete event, and system dynamics, and integrate them all into one model. We have been able to show that it's possible to create self-configurable models, to dramatically cut the development time, as many of you have shown, is provide the customer with a template. They populate the template directly out of their ERP system or out of their MES system, and it automatically builds the simulation model for them. And a few of the examples that we showed today, we did exactly that. That means that these models are reusable and can scale very quickly. And lastly, the ability to create standalone apps that users can run on their own desktops, that has beautiful user interfaces that are easy to use. Simulation can be very daunting. For newcomers especially, they don't want to break it, they don't understand it, it's too complex. So the ability to build beautiful, easy-to-use interfaces is absolutely critical. And then, of course, with the new AnyLogic Cloud, being able to run these models, very resource-intensive models up in the cloud. So what was the business case specifically for the models that we've built? I mentioned that we've ended up building 4 models. 2 of those models were built by Jaco-Ben simultaneously, which is really challenging, and you'll share a little bit about how much fun that was. And 2 of the other models were built by Andrei Malikanov and his team. Again, incredible models that have been built that I'll show a little bit later. So I'll hand over now to Jaco-Ben to take you through the first 2 models.
Thank you, Alan. So the first model we're going to show you guys is the hot coil finishing area. Now, this is a specific point in the supply chain, and what's great about having this detailed model is that we were able to test some of the assumptions that we got out of the integrated supply chain model. So this area had significant congestions before we started with this project, so much so that they actually created 2 new storage locations. One was called Car Park, and the other one was called P Field. So the business case for this model was to determine some of the impacts of some of the investment choices that was already made, like increasing the output out of the hot strip mill, but also to see whether or not they will get the benefits they would think they were going to get out of making some operational changes, like creating double width coils, so you reduce the number of coils that you output out of the mill. And the other one was upgrading their current wagon fleet. So some of the insights that we gained through this project is that we discovered that for every rule that you ask them, how is this rule made up of, they say, well, it depends. And I assume that's nothing new to any simulation modeler. And it was really difficult to model these rules because none of them were formally documented. So one of the benefits out of this model was to say, well, here's at least some form of a flow chart or presentation or some documents saying these are the best practices across the different shifts, how they sort coils in this area. We also identified some of the best options to reduce congestion during some of the peak times, so upgrading one of their conveyors and diverting coils to a different workstations. We also identified that the lowest cost option between the 2 options that they had for upgrading the wagon fleet actually yielded the highest total cost of ownership and actually increased the congestion. We also quantified the impact of changing the product mix, as I mentioned, which is the double width coils. And we tested some other diversion options that was coming out of the supply chain model. Of all the demos we're going to show you guys, it's only brief functionality snippets out of the model. Most of the functionality is embedded across all the models, things like scenario comparison functionality, detailed 2D animation, as well as 3D. So in this specific model, we had a nice 2D view, which you'll see here, showing you all the coils in the system. They were able to view it by the different coil types and the destinations, as well as whether or not the coils were actually stored in the correct location, which you'll see here by the red and green coloring of the coils in a moment. And so it is interesting to see even the simulation couldn't place all the coils where they wanted it to be placed because there's too much congestion in the system. So what happens is, and you'll see shortly in the 3D, is that if you place a coil on top of another coil, the next time you want to remove the coil that's at the bottom, you have to dig out that coil. So now you take up time of a crane operator or some other resource, having to pick up the top coil, go and place it somewhere else. Now you don't have space in that location anymore. Now you need to take that coil, move it a couple of 100 feet away somewhere else, go and dig out that coil at the bottom, place it at the next workstation or at the wagon. And in the end, this wastes a lot of time, and you end up moving coils around the whole time. Instead of being able to run with fewer coils, you can do everything more efficiently. So the 3D animation was also really nice for doing the validation of the model. The scenario comparison functionality was really helpful in this setup because the guys could set up multiple scenarios in terms of demand and product mixes, select all the Excel files, set the number of replication, select run all. They let the model run overnight. You'll run all the replications. You're able to view the statistics. And in some of the charts at the bottom, we output the individual model runs. So you can see if there were specific abnormal occurrences. You can see whether the results for this specific scenario was valid. This functionality is obviously, as I mentioned, incorporated in all other models as well. So the next model we want to showcase is the steel and slab part of the model. So the steel operations, for those of you who are familiar with the steel plant, starting at the blast furnaces where you've got your liquid steel coming out, all the way to the casters, is incredibly complex. And it's very difficult to test the impact of changes in product mixes or operational rules that you want to change. So this was great for testing some of the new operating philosophies, changing the speed restrictions on casters or upgrading some of the treatment units. The insights gained here include some of the learnings that we got just from modeling the scheduling logic. And we were able to test some of the caster speed restrictions and upgrades that they wanted to do, alternative prioritization rules for different products being produced at different casters, as well as different maintenance strategies. And one of the big questions that they had was, what if we produce some of the more complex products? There's a bit of a higher margin on them, but it really messes up the flow through the entire system. And we were able to quantify that to them and say, listen, the maximum capacity of high-grade electrical steels that you can make is X amount of tons. So in all of these models, we also had a detailed input sheet. Like once you've loaded the Excel sheet, you're able to see what is the curve for the demand that you've loaded and what's the different product mixes, etc. For this model, it was key that we had detailed 2D animation and that the user can click on a crane or a specific product at any time to see what's the status of that product and whether or not the model is routing the product through the correct stations and making the right decisions whether to cancel that product or not. And at the heart of this simulation was the scheduling logic. And as you can see there in this complex Gantt chart, every heat that flows through the system needs to book a point on an appropriate treatment unit. And you can't release that heat into the system unless you know you're going to have that unit available at the correct time. Otherwise, you're not going to adhere to the technical specifications that a product can wait before and after treatment. So this layout, although it's very complex and I can't go into it now, is similar to the MES system. So they were able to look at this and say, well, this looks good. It seems like the model created a reasonable plan for these products. And we were able to simulate the forecasted and actual hot metal supply and the standage of the liquid iron at the top, as well as create functionality to do manual scheduling. So part of the validation, we can say, well, to an operator, okay, this is the current product mix that's required to be made. How will you make it? In what order? What treatment units would you book? So it was really useful for them to see this visually and able to validate that, yes, the model is an accurate representation of reality.
Thank you, Jaco-Ben. Just a few points to mention here. Jaco-Ben mentioned this idea of you are interviewing the experts to try and understand what are the rules that they are currently using. And that is, of course, as you know, critical in terms of our data validation and verification. We want to prove to ourselves and to the management team that we've built a model that can not only accurately reflect the impact of changes, but can accurately reflect what the actual performance were in the past. With this level of complexity, we were able to create a model that was within 2 percentage points accurate to predict what the actual tons produced was over the last year and what the actual inventory levels were at the various stages. And you can think about the complexity of that. It was an enormous challenge and a real privilege to work on this. Jaco-Ben briefly mentioned the idea that every time you ask somebody, so how does this work? What's the rule that you used to schedule this? The answer would always start with, it depends. And if there were 2 people in a room that were both operators, they had different rules. This tacit knowledge that are sitting in people's heads that have been there for 20, 30 years is most likely will be lost if you don't do these type of projects. To force them to verbalize these rules so that we can digitize them and check them. And then people can learn from each other, from different shift patterns to say, oh, I've always scheduled the crane like this. I see your way in some conditions work much better than mine. Jaco-Ben also mentioned just briefly about the idea of the car park. And that literally means the car park. The first time we arrived at the steel plant, we couldn't find parking space. Why? Because it was filled up with coils, right? Remember the idea of asset utilization? What happens if you're trying to maximize an asset that's not a bottleneck? You produce stuff that's not needed. Where do you store it? Turns out a car park is a pretty cheap way of storing it. One of our own success criteria, by the way, was now we go there, there's lots of space to park the car. So in terms of the overall supply chain model, our specific objective was here. They wanted to implement a theory of constraints-based supply chain solution across the board. So that's what order fulfillment strategy do we need? Do we make to availability? Do we make to order? Do we make to forecast? How can we test that? And we use the simulation model as a way of testing those rules. Once tested, we can check what the optimum parameters are, and those are then in parallel being implemented into their SAP system and MES system. So specifically related to the supply chain project, we wanted to understand what was the real causes of the congestion that they were experiencing, especially over the last year. There was literally coils everywhere. They couldn't get anything out. So throughput was dropping, lead times were growing exponentially, and a huge amount of inventory. We wanted to check what the global optima rules should be and provide them with a decision support tool that's not just a once-off tool, but a tool that they can use on a weekly and monthly and annual basis to make critical decisions. Some of the insights based was they had developed this incredibly complex algorithm to their sales team that when a salesperson receives an order, the system generates for them what are all the possible ways of manufacturing this coil and all the possible ways of distributing this coil. Now, of course, the salesperson had to make a selection. So they provided a prioritization way of presenting these options based on lowest cost per ton. And guess what they were doing? They were always selecting the lowest cost per ton option. This database was never updated with what is fixed versus variable cost. So it was causing a systemic bias towards certain manufacturing and distribution routings. And that's where a large part of the congestion came from. The other part was over time, because they'd been debottlenecking, they were ending up with balanced capacities, and that by itself will cause congestion. We also used the model to validate some of the key decisions that they thought were risky, to process things on alternative processing units, even though their own system was saying it was more costly. The system not only validated that, but said that you should have made those decisions a month or two earlier already. And we also used it to check decisions around, will the investments that they're planning actually increase the output? Will they get the benefit because they just couldn't afford to not make reliable commitments in the past? We'll just quickly show you this model, incredibly complex model. This is one of the models that Andrei Malikanov and his team built for us. So as the model is showing, the first thing is completely parameterized. So you open up the model by opening up an Excel spreadsheet, essentially, that has been completed by data that was collected out of their ERP and MES systems. incredibly complex, over 70 worksheets of data to fully describe the system. Because we are modeling every part in the supply chain and lots of detail inside, campaign runs, which WIFs can you do where, what happens if you switch over from one grade to another type of grade. You can see the overall supply chain there and lots of statistics that really helped with the data validation side. We first wanted to check that it could accurately represent the throughput that they were getting, the inventories and the due date performance, which was around 60 to 80%, and very quickly we were able to do that. Every single part of that is sort of look inside, so you can click on a link in the supply chain. It will take you to the process chart inside. You can see what the stock levels are. You can see what the processing units are. We've developed critical functionality that also shows us what's causing the high WIP. Where is it coming from? Is it coming from a downtime event, or is it coming from somebody releasing more because of a large batch early on in the supply chain? We then looked at the various stock levels at the service centers. We created theory of constraints algorithms to check if we can reduce the shortages and surpluses. These algorithms are learning from experience to decide when to increase or decrease stocks. We're presenting full financials to them, so their finance team was very interested that they can use this to make annual commitments regarding what level of financial performance can be committed to. We can show it from a customer perspective, what is the service levels that can be achieved by simply changing a few rules in the way that we are scheduling this facility. So an incredible amount of background statistics that are being gathered that really helped a lot. There you can see how the slab stocks increased, and that's where it started. It's going to cause, first of all, fill up all the formal storage areas, and then later on. Simple things like just being able to sort dramatically, tremendous amount of functionality to understand what is happening inside of the system. So that is our supply chain model. I want to just highlight one area that we use the model to really challenge an industry paradigm. There's a paradigm that says, considering the high cost of a tundish change, which is out of the cost, every time you're changing a product grade and width, you have to change this. It's about $5,000 a change. What would happen to the cost per ton if you are moving more towards a demand-driven system where you are only making what has been sold rather than selling what has been made? What will happen to the cost of ton if you start cutting down your batches? So this was the financial performance with the current system that says minimum you should run heats is about 6 before you can afford to make a change, up to a maximum of 11. Of course, the 11 is if I run too long batches, I'm not getting to the stuff that is really required. And that was the level of profitability that they could achieve, the level of cost per ton. You'll see there about $407 a ton, and average service levels about 86%. This is what happens if we remove that limitation. Rather than the cost per ton going up, because we are creating more throughput, by only producing what is really needed now, the cost per ton goes down quite substantially. Profits are up, cost per ton is up, service levels is up significantly, and lastly, very importantly, that the number of hot connects that you can do is also dramatically up. That means that I don't have to cool down the steel before I can process it the next. I can process it while it's hot, and that has a huge energy saving implication for this business. So in summary, it was a really exciting project. It really stretched the limits of our own capability, and I think of any logic sometimes. We had incredible help from a large number of team members. Andre, if you can just stand up. Andre and his team did an incredible job. There was many, many late hours that we were working on this. So we'll open it up for questions if there are any questions now. Thank you very much.
Really, really cool, really impressive models. I've got a very specific question because one of my clients, I built a similar complex model about the crane movements. Do they have like collision avoidance? Because that's something we struggled with, like intelligent crane movement that takes into account physical constraints. How did you handle that?
Yeah, so it does take into consideration the physical movements, but the one thing that it doesn't do is if one crane is already moving, so it's already got a movement assigned to it, and at that moment that it was assigned, it was a higher priority than what was the other movements that was available for this crane. It will first finish that movement before this crane will be allowed, and then you do another check, like who's got the highest priority movement now. Whereas in real life, it might be the case, not so much in the steel model, but definitely in the coil model, where a crane would get a job. It's saying this is the highest priority job, pick up the coil, and while it's busy moving, they say, whoa, a train has just come in, that is a higher priority. You actually go and put that thing down again, or just go and place it somewhere else, not the original destination you identified, because they're going to start doing some loading activities here. So all of that functionality we had to custom build. But the limit ends where as soon as you assign the movement, it first finishes it before you check again.
So very impressive model. Lots of variability, it looks like. A ton of variability in there. Were you concerned about run speeds once you went into doing the experiment modes? How long it was going to take to get some reasonable confidence intervals on the outputs and all that?
Yeah, this is one of the things that our team worked a lot on. The model that we didn't show had an additional level of variability because that was producing electrical steels that have huge question marks about yield. So you don't quite know how much to launch in order to get out what you're looking for. And once it goes into that system, you have to get it out. So it was something that our teams worked really hard on to get the run times down to around, depending on the type of model, between 5 minutes to about 10 minutes per scenario. Any more questions?
Anybody else? Otherwise, I go a second time. As I said, I built a really similar model, and you say plus minus 2% to reality. We achieved like maybe 7 or 8% in our model. And when I hear 2%, I get very skeptical. So how did you make sure that you're not actually overfitting? Because you said you've got the operator heuristics, how they behave. You modeled that in reality. But there's lots of variability there of how they actually behave. So 2% there, how did you avoid overfitting?
To be honest with you, even I was surprised. I was hoping for about 5%, especially on the inventory levels, but it was just a very systematic approach. We would run the model, investigate, and that's where all the statistics were critical. What caused the difference? This is how much you actually did. This is what the model said you would have done over that time period. Can we find out what the critical differences are? And I think to some degree we were lucky in that there were a few things that made a big impact because as you rightly point out, there's lots of variability. So I would have been quite happy with 5% and it was quite surprising that we could get it down to about 2%.
So just to add on that, I had a discussion with Andre about this just before we presented as well. So and you can maybe discuss with him a bit more. So especially in the supply chain model, when you're checking the stock levels and the inventory and you're comparing and you say, oh, well, here's an abnormal event that occurred in reality. So obviously here we find a great deviation. And then you say, well, the rest of the model won't be verified because this is going to impact everything that's going on. So we'd input a manual event that simulated what happened in real life and then simulate further until you find another event. So we manually added some of the abnormal events into the model as part of the verification phase only.
Yeah. Any more questions? So just in summary, a really, really exciting project for us, incredibly complex models, but we were able to present it in a simple enough way that the management are now using these models on a weekly, monthly, and annual basis to really guide their decision making. In parallel to this, there's an implementation going on in their SAP system. So these models have informed them what are the rules to manage and optimize the system rather than subsystems. And those are being implemented into their SAP and MES system. So thank you very much again for the opportunity. Thanks.